In this lesson, we take a closer look at divisive clustering. We go over divisive clustering algorithm, splitting strategies, and extensions to hierarchical clustering. Divisive clustering starts with all data points grouped into a single large cluster. From there, the algorithm recursively splits the cluster into smaller and smaller subclusters. This process continues until each data point forms its own cluster or until a suitable stopping condition is met. A well-known algorithm for this approach is called Diana, and it's implemented in statistical analysis packages like S+. Additionally, divisive clustering can be considered a global approach since all the decisions are made starting from the entire dataset. When it's compared to agglomerative clustering, divisive clustering can be more efficient because at each step, the algorithm only focuses on how to split the clusters rather than consider many possible merges. However, the splitting process presents three main design questions: which clusters to split, how to split, and where to stop. Once multiple clusters have been formed, the method needs to determine which cluster should be divided next. A common strategy is to compute the sum of squared error for each cluster. Then the cluster with the largest sum of square errors is chosen to split, since it exhibits the highest internal variability and is the least cohesive. For the splitting criterion, a practical approach is to use Ward's criterion. Here, we evaluate possible splits and choose the one that results in greatest reduction in sum of square errors. For datasets with categorical attributes, measures such as the Gini index can be used. For handling noise, it's not always meaningful to continue splitting until every object becomes its own cluster. For example, if a company like Trader Joe's is analyzing customer locations, then splitting beyond a small neighborhood may no longer add value. To avoid producing extremely small or noise-dominated clusters, the algorithm typically employs a termination threshold, which prevents splitting when the resulting subclusters are too small or mainly noise. A key weakness of divisive clustering is that it doesn't scale very well. A naive implementation may examine many candidate splits, which may end up with a complexity of big O n squared, infeasible for large datasets. To address the scalability issues, several influential algorithms emerged in the late 90s to extend hierarchical clustering, which includes BIRCH, which uses a data structure called CF3 to incrementally adjust the quality of subclusters, Cure, and CHAMELEON. In summary, we discussed divisive clustering.